Welcome back. So if you remember when we learned about writing isomers for an alkane, okay, let's revisit that concept and then tie that concept to the idea of free radical stability and then making products through a free radical reaction. All right, so let's say if I give you, this is our given compound, okay? Now, if you notice right away that it fits perfectly into our alkane general formula of CnH2n. That is, if I put 5 here, okay, then I would get H12. What that means is my compound does not have a double bond and it is an alkane, right? To be precise, it's a pentane, right? Now, if you remember that we can write multiple isomers for this, right? And one of them would be this. Right? Now, this is the straight chain parent compound, right? Now, we could go one step ahead and do this, which again, this is all something we have learned. So I don't want to teach you how to write an isomer because that part is already over. We are now moving to the next stages of it. So this would be one of the possible isomers. I'm writing only the ones that I want to write here because that way I can explain the concept that I want to really get it across. So what if you reduce one more carbon? Then we are left with this, right? And then perhaps let's write one more just for good measure. Okay, I think that's pretty much all we can write at this point for the concept that I want to drive across. So let's take this one, okay? And if we compare this directly to the straight chain, that means we see that we do have, if I react this compound right here, okay, the CH3, CH2, CH, CH3, and CH3, okay? Now, if this were to first, let's actually write it this way, okay? Let's write it this way so that, again, for time being, I'm showing you the full structure, but then as we learn more and more, I would resort to condensed line structures, okay? So here we have 2 electrons, okay? Now, again, as always, this is going to react with the chlorine. So the chlorine is going to, under light sources, would generate 2 chlorine free radicals, right? The first free radical would react with probably, again, I will come back and tie this concept, but for now, I'll just take this hydrogen. You can ask me, why did I just take that hydrogen? Because that's the concept I want to drive across, okay? So this combines with this, okay, leaving you with this, okay? Now, plus HCl, right? Now, the other chlorine radical then would combine with the free radical that we just generated. Now, if you notice, I'm going to put this in this little bracket. What this bracket means, it is an intermediate, okay? Typically in chemistry or other branches of science, intermediates are usually denoted within square brackets, okay? Now, this chlorine radical would then combine with this, and then we will generate our final product, which would be this. Right? Now, what did you observe here? Remember, I specifically picked this hydrogen Why? I could have picked this, this, or this. Okay, we're going to look at different combinations of it. Okay, but what type of radical is this right here? Okay, I'm going to circle that in maybe a pink. Okay. If you go back to the previous video, I did suggest a carbon with no hydrogen, essentially, right? This is very similar to what a carbon, okay, with any group but no hydrogens, okay, no hydrogens, okay. We call this a tertiary, okay. This could be all CLs or it could be something. I'm just going to put X, Y, Z, okay. Could be anything but no hydrogens. We call it a tertiary free radical, right? And we notice that in our stability sequence, that the tertiary free radical is the most stable of them. And that's why I chose, out of the three isomers, I chose to describe this one, because this is the only combination out of all of them that could generate a free radical. If you don't believe me, take the other combinations and try. Based on the three combinations of isomers I've written in blue, this is the only one, if I get rid of this hydrogen, would generate a free tertiary free radical, which is the most stable of them. Okay, now what if we now we'll pick that same isomer, okay, but what if this time around, instead of that hydrogen that I chose right from the get-go, what if I chose one of these two hydrogens? I mean, they're identical. I'm just gonna, for time being, I'm just gonna pick this one. Instead of writing it as CH3, I'm just gonna write it as CH2 hydrogen. I mean, it's essentially the same thing. So now this, when it reacts with the chlorine radical, again, let's go get our red. Okay, so we can have multiple combinations, which is what I will test you, okay? And then, so we will have this as our intermediate. Sorry. This will be our intermediate. Anything with a free radical still on cannot be the final product, because free radicals are unstable as it is. Okay, that's why they try to get into some sort of form where they can be a product. Now this is where we are, and again, just like I did last time, I'm going to box this in red, called meaning intermediate, means this is not stable yet, but it would like to get stability. But if you remember from our stability sequence, I'm gonna color this in pink right here. Okay, and if we had removed that hydrogen, then we got tertiary free radical. Because we chose to remove this hydrogen, this carbon is attached to two hydrogens and a free radical. And if you remember, I called this the primary free radical. Okay, primary free radical. So that is a carbon with at least two hydrogens. Okay, carbon with two hydrogens. Okay, and a different group. It could be anything, just like in this case, this X could be this whole thing right here, but it's got two hydrogens. That's what you need to focus on. Don't worry about what the X is, but focus on the two hydrogens. Now, we clearly know that the product that we generated in the previous case is definitely more stable, because the tertiary free radical is more stable than a primary free radical. However, this will be a minor product. Okay, in organic chemistry, something we have not learned yet, but we will consistently bring up that discussion, is whether a product made would be a major product or a minor product. Now, if a product is directly out of a less stable form, then this would be a minor product. Okay, and the product we generated earlier, which is, I'm going to just write this here so that you can see it. Okay, this is what I had. This right here is a major product. Why? Because it's the free radical intermediate that governs whether the product would be a major or minor product. Now, let's say we pick this hydrogen. Okay, this is just a lot of combinations on why organic reactions, if it is a really efficient reaction that's been designed, then you will have less of the minor products. You go straight to the major product, but it is not always possible. Okay, what if we pick the same, but this time around, let's focus on, okay, let's focus on this carbon with the hydrogen. We've looked at a primary, we've looked at a secondary. We've looked at a primary, we've looked at a tertiary, but we've not looked at a secondary one. Let's go through that. So what I'm going to do is get rid of this 2 and write this as hydrogen in this form. Okay. So now what happens? So let's go get our chlorine. Okay. The chlorine, one of the chlorine dot reacts with the with one of the electrons, just like how we've been doing. Okay. And that leads to CH3, CH dot, CH, CH3, CH3, right? Again, keep in mind, this right here is a intermediate, okay? As I repeatedly said, while there is relative stability between free radicals, all free radicals are unstable and they like to get to a product as quickly as they are made, okay? So what does that mean? So let's go get our other Cl dot. So in the process, we made HCl also as a product, and the remaining Cl dot combines with the free radical on the carbon, right? And then that leads us to the other combination of the product that is possible, which is CH3, CHCl, CH, CH3, and CH3. Okay, now if you focus, okay, we have now officially learned a secondary free radical as well. And what is a secondary free radical? Okay, a carbon with at least one, it has to have one hydrogen and 2 other different groups. Now if you notice, the X could be this and the Y could be this, or Y could be, X could be this and Y could be this. It doesn't matter which one you want to pick, because we're not doing anything else other than identifying that a carbon has only one hydrogen. Now this is a secondary radical. So this would be a little bit more stable product over this, but it still would be less stable compared to the major product. Okay, so this would be the intermediate product. Okay, not intermediate as an reaction intermediate. This would be intermediate between the primary and the tertiary. Okay, so that's the point. I've already shown you how to do the methyl one because we started with the methane. Okay, so now we have learned all these 4 things. Let me give you a practice exercise. Okay, now this time around, I won't show you the full skeletal structure, but let's just say, this is my condensed line structure. Okay, and now if this were to react with the chlorine in presence of light, okay, write all possible products, okay, products, and identify, there may be more than one major product, but then we'll get to that later. For now, identify major and minor products simply based on the fact whether the products were generated from a primary, secondary, or tertiary free radical. Okay, again, you may have to go back to the previous video or even little rewind on this video to actually remember which radicals constitute primary, which constitute secondary, which constitute tertiary. And when you have that information, then you know what will be the products. Okay, this is pretty straightforward, and I will probably stop the video here, and in the next video I will try to give a solution for it, but then I will hold on to it because we will also practice some of these problems in class, but I will have a solution for this particular reaction in a separate video. All right, so stay tuned, and I'll see you with another video. Bye-bye.